There are a number of different ways to find the prime factorization of a number. What I'm going to show you will be using a factor tree. So let's say I want to find the prime factorization of 24. So my goal here is to write 24 as a product, multiplication, of primes. So here is what I'm going to want for my final answer. Now, with the factor tree, I'm going to start with my number 24, and I'm going to come up with any two factors of it. So I might see 24 as 3 times 8. You might see 24 as 4 times 6, and someone else might see 24 as 2 times 12. So these are the start of 3 different factor trees. Well, the person who started with 3 and 8, we look at each factor there. When one is prime, we circle it and stop. So 3 is prime, only factors of 3 are 1 in itself. 8 is not prime. 8 can decompose into 2 and 4. Multiply as 2 times 4. 2 is prime, only factors of 2 are 1 and 2. 4 is not. 4 can be factored as 2 times 2. So here, for 24, I've got 2 3 times, so 2 to the 3rd power, times 3. If someone else did 24 as 4 and 6, well, 4 is not prime, so we can break that down. 4 is the product of 2 and 2, both of those are prime. 6 is the product of 2 and 3, both of those are prime. We get 2 cubed times 3. If we did 2 and 12, 2 is prime, 12 is not. I could factor 12 as 3 and 4. I could factor 12 as 2 and 6. If I use 3 and 4, 3 is prime and 4 is 2 times 2. Once again, I've got 2 cubed times 3. So 24, prime factorization is 2 times 2 times 2 times 3. This gets us the fundamental theorem of arithmetic. Tells us that the prime factorization of a natural number is unique. Primes are used in number theory, in cryptography, and you could find some interesting things if you read up on prime numbers. But again, there are many different methods for getting prime factorization, but there is only one correct prime factorization of a number, and you can check by multiplying that out. You may also, I've got a link online, and the Wikipedia article on this is pretty good too. The sieve of Eratosthenes is a method for finding prime numbers. It'd be good to take a look at that and be able to reproduce it so that you can find all the prime numbers under 100. Knowing, say, the first 25 primes can be very helpful to you and useful. Okay. So let's check a couple others here. If I'm trying to find the prime factorization of 150, well, we know then that if we use a factor tree, there are a number of different factors we could start with. We don't need to start with a prime, we just need to start with any two numbers. So this is where divisibility tests come in. 150 ends in 0. If the number ends in 0, I know that 10 is a factor. So that's going to be able to let me break this down a lot easier. 150 is 10 times 15. Anytime you have an even number, it's divisible by 2. If the last digit is a 0 or a 5, the number is divisible by 5. 10 is 2 times 5. 15 is 3 times 5. So 150 is 2 times 3 times 5 times 5. I could also write that as 2 times 3 times 5 squared. For my purposes, I'm going to leave it written out with each product. If we're trying to find the prime factorization of 351, well, 351. My number is odd, so it's not divisible by 2. Not divisible by 5 because the last number isn't a 0 or 5. Likewise, not divisible by 10. So I may have some trouble here getting started. The divisibility test that becomes most useful here is if I sum the digits. 3 plus 5 is 8. 8 plus 1 is 9. 3 divides into 9. So 3 is a factor of 351. This works for 3, it works for 9. The sum of these digits is a 9. 9 is a factor of 351. So if I do 351 divided by 9, 9 goes into 35 3 times. $81. So 351 is 9 times 39. 9 is not prime, but it's 3 times 3. 39 is not prime, but it's 3 times 13. 13 is a prime number. Only factors of 13 are 1 and 13. So 351 is 3 to the third times 13. And one comment, 1 is not prime, it's not composite. It's the only natural number that doesn't fit into the prime or composite. All other natural numbers will be either prime or composite. Now, an application of the prime factorization and there will be a number of these, but simplifying fractions. If I have 150 over 351 and I'm trying to reduce this, well, I can use the prime factorizations, which I've just found. 150 is 2 times 3 times 5 times 5. 351 is 3 times 3 times 3 times 13. I can see that a 3 is a common factor, and that's the only common factor. So 2 times 5 is 10. 10 times 5 is 50. 3 times 3 is 9. 9 times 13 is 117. And by using the prime factorization, I know, because the numerator and denominator have no primes in common, I know that this is the simplified form. This is reduced. Doesn't matter what I try to divide both numerator and denominator by, there is no natural number that will divide evenly into the numerator and denominator, because we've listed all possible prime factors here. So that can be a way to be sure you've got a fraction that's reduced. This will prime factorization will also come in handy when we're dealing with radicals and simplifying radicals.